phone, your Wi-Fi, satellites, radar. Have you ever stopped to wonder how antennas actually work? It might seem like magic, but it is all pure physics and engineering. In the next few minutes, we are going to break down every key antenna parameter so you can understand exactly what is going on. First up, let us talk about the radiation pattern. Think of it as the antenna's fingerprint, showing where it sends its energy. It's an ideal isotropic antenna would radiate equally in all directions, like a perfect sphere, but that's physically impossible. In the real world, we have directional antennas that focus energy in one specific direction, and omnidirectional antennas that provide 360-degree coverage, like your Wi-Fi router. We describe these patterns with terms like the main lobe, which is where the strongest signal goes, and smaller side lobes and back lobes. This helps us understand how energy spreads out in both the near-field and far-field regions. Now, how do we measure the strength of this energy? We use two key metrics: radiation power density, which is the power spread over a square meter, and radiation intensity, which is the power per solid angle. Together, these tell us exactly where the antenna's energy is concentrated. This brings us to directivity and gain. Directivity is a measure of how focused that main beam is. The more focused, the higher the directivity. Gain takes this a step further by factoring in real-world losses. It is the directivity minus any energy lost to heat or other inefficiencies. This is where efficiency comes in. It tells us what percentage of the input power is actually turned into useful radiated energy. Ever heard of half-power beamwidth? It is simply how wide the main beam is, measured at the points where the power drops to half its maximum. A related concept is beam efficiency, which compares the power in that main lobe to the total power radiated. Generally, a sharper, narrower beam means a longer reach. Of course, an antenna does not work at all frequencies. Its bandwidth defines the specific range of frequencies where it operates effectively. And just as important is polarization. This describes the orientation of the electric field wave. It can be linear, circular, or elliptical. For two antennas to communicate, their polarizations must match. A mismatch leads to something called polarization loss factor, which means wasted power and a weaker signal. To get power into the antenna in the first place, we need to consider input impedance. This has to be matched to the transmitter to ensure maximum power transfer. On the receiving end, the vector effective length and effective area explain how well an antenna captures incoming signals from the air. Finally, all these parameters come together in powerful formulas. The maximum directivity and effective area are crucial components of the Friis transmission equation, which calculates the power received by one antenna from another. They also power the radar range equation, which helps determine a target's distance. We even consider things like radar cross-section and antenna temperature. As you can see, antennas do not guess. They obey the fundamental laws of physics.